Hi, my name is Daniel and I'm a PhD student at the Technical University of Munich. In this work, we present challenges we faced when developing microRTS, a regression test selection technique for end-to-end tests in microservice-based software systems. We performed an initial case study on the German COVID-19 contact tracing application together with our industry partner T-Systems. We find that for manual end-to-end testing, the preciseness of test specifications really matters. Contrary to prior studies on regression test selection, we find that method-level granularity of per test execution traces seems to give the best results in this context. Let me start by giving a brief introduction into regression test selection. Regression testing is a regularly performed software testing activity to ensure that changes have not unintentionally affected the existing system behavior. So say you have a program, you introduce some changes, and you have a test suite that you want to re-execute to make sure you did not introduce any problems. The problem with this is that it gets too costly to execute every test after every change, specifically when the test suite grows and also when we have limited testing resources. Test selection or regression test selection tries to identify only the relevant test cases for the introduced changes and then execute only that subset of the test suite for those changes. In microservice applications, we face a few problems that make this more difficult. First, contrary to unit tests, we may also have some system boundaries that are being crossed by the test. So we need to make sure we know what a test is doing beyond one single system. And this may also expose us to different programming languages. So we need to make sure that we understand what the test is doing, what kind of programs and what kind of programming languages it is exercising throughout its execution. Moreover, it could also mean that we have multiple services and multiple clients that need to be considered when we perform test selection. Moreover, there is several studies on RTS in distributed systems already, but they lack discussion on the instrumentation overhead, which may preclude the applicability of RTS overall. And also, most regression testing research so far addresses mainly automated unit tests, but complex scenarios, especially in these microservice-based software systems, are often tested manually. And there's first evidence that shows that RTS might behave different and might have different trade-offs for manual testing. To solve some of these problems, we introduce microRTS in this work. And microRTS is an RTS technique that is suitable for such microservice-based systems. At its core, it exploits existing distributed tracing infrastructure, and it uses this to observe what a test is doing at runtime and use that information then later on for test selection. So, as I said, distributed tracing is the backbone of microRTS, and it uses the concept of context propagation, which is introduced by distributed tracing infrastructure already. And to make use of such distributed tracing infrastructure, we can harness the popular distributed tracing frameworks that are around. In this case, we use OpenTelemetry to implement microRTS, and it allows us to have the context propagated across different services and clients and always know what request belongs to which context. So we can start a new context for a specific test that starts, for example, on some mobile application, and then we can trace what this context is doing, what services are visited, and when it returns to the client, and then we know what this specific test case has executed. The second basic building block of microRTS is code instrumentation. And this is due to the fact that distributed tracing alone does not perform any instrumentation of the source code that we can use. It merely collects basic metrics such as response time and lets us propagate the context across different services. But we need fine-grained test execution information. We need to know what a test is executing. And specifically for the use case we're looking at, we require method-level instrumentation. Why is that? Well, consider a system under test that you start once in the beginning and then you run your entire regression test suite against that one deployed system under test. So it might be that objects are created on the first test case and they're reused across all the following tests as well. And therefore, if you only instrument object creation, we would miss these covered code parts that are used throughout the tests that are subsequently run. So we need to instrument the methods of the objects here. Moreover, we require some kind of parameterization of microRTS to check what are the implementation aspects that are better in terms of overhead. So for example, we want to consider, is it more efficient to collect, to export coverage probes to a file? Or is it more efficient to send them via TCP socket to some central collector that will then collect all the covered methods or classes? And this is an implementation aspect that we want to evaluate with microRTS. And therefore, we introduce these parameters to microRTS in order to make sure that we can properly evaluate it later on. Moreover, microRTS needs to support microservice instrumentation, obviously. And for our case study that I will present later, we require it to be able to instrument JVM languages, microservices written in JVM languages. And also for our case study, we require it to instrument Android mobile clients properly. Here's the overview of the microRTS architecture. So as I said, we have the system under test, and it may consist of a client and multiple microservices. And we collect coverage information, in this case, either method or class level, depending on how microRTS is parameterized. And then we collect that information either by dumping into files, and then the trace collector will collect it from there, or we send it via TCP socket. And that's again, depending on the options that you provide microRTS with. All right, let's go into the evaluation of microRTS. And as I said, one important aspect that we want to evaluate is the efficiency of microRTS. And the research questions here are, firstly, how much instrumentation overhead does microRTS introduce at system startup and during testing? And secondly, how does the granularity of coverage probes and their export strategy affect the instrumentation overhead? To evaluate microRTS and to answer these questions, we performed experiments on the T-Store. T-Store is a popular microservice benchmark application, consists of 6 Java microservices. And we wrote 23 automated end-to-end tests for the T-Store. They were also merged into the main code repository of T-Store, so further research can also use them. And we then ran our experiments with the different parameterizations of microRTS and repeated the experiments 30 times, measured the average runtime, compared it with a non-instrumented baseline. The results look as follows. First, for the first research question, we see that during system startup, microRTS introduces an overhead of 67.5%. And by having a closer look and also running it only with the OpenTelemetry instrumentation, we see that 40% actually already come from OpenTelemetry. So they're just required to have the distributed tracing in place. During testing, we see that microRTS introduces 18% of instrumentation overhead, runtime overhead, and again, 10.5% already come from OpenTelemetry. What we can also observe is that, I mentioned it earlier, the first test has a significantly higher overhead. And this is due to the creation of objects that typically takes place in the very first test that is being run. And it's also related to the nature of dynamic bytecode instrumentation in the JVM, because typically the class loader will load the bytecode file on the first test execution, and then it will transform it for the instrumentation. And then on subsequent tests that are being run against the system under test, these have already been transformed and instrumented. Regarding the second research question, we see that the granularity of method level only introduces 1.2% compared to class level. And there's a note, so instrumentation still has to take place at method level for both of these granularities. But the question is, how often do we export these covered probes? So if there is a new method being covered, do we actually export it? Or if there has already been some other method inside that class being covered by the test, then we do not have to export it for the class level granularity. So it's just a matter of how often do we export the probes and how fine-grained do we store them. Regarding the export strategy, we see that the file strategy only introduces 1% of runtime overhead compared to the in-memory baseline. So that would mean we keep all the coverage probes that are being covered in memory and then only dump it at the very end when all the tests have been executed, which is questionable on large systems because your memory capacity might not be enough. And for the socket export strategy, we see that it introduces 6.7% compared to in-memory, which is significantly higher than the file export strategy. So we see that file is rather inexpensive, and that's somewhat surprising because of the involved I/O. All right, let's talk about the case study that we performed to measure the RTS effectiveness in a real software system, in a real-world software system. And we looked at the German COVID-19 contact tracing application. It's an open source project, has roughly 170,000 lines of code written in mostly Java and Kotlin. And we consider a subset of 7 microservices that are publicly available. And we consider also the Android application that is used to serve as a client for the regression tests that are being run against the entire software system. From our industry partner T-Systems, we got 20 manual end-to-end regression tests, and we then used those, we then executed those end-to-end tests manually on one version to collect the per test execution traces that we need for the test selection of subsequent releases. Then on the subsequent releases, there are 12 release candidates between version 2.5.1, where we collected the traces, and 2.6.1, we evaluated the test selection. And for the evaluation, the research question is how much manual end-to-end testing effort can we, reduction can we achieve with microRTS? And the algorithm for test selection is rather simple. It's based on prior research. If a class or a method is in the change set, we select all the tests that have this class or method in their per test execution trace. The results show that at first, all 20 tests are selected for method and class level RTS for all versions. And we then take a closer look at the selection results and see that they are actually all caused by changes to the client code. And this underlines the importance of client tracing. Furthermore, all test traces include shared covered methods from the home screen, although not all 20 tests actually test functionality on the home screen. And this made us suspicious, and therefore we refined the test traces and excluded the irrelevant methods that are just there because the home screen was covered for those tests that do not check any functionality on the home screen. And then we reran our test selection and saw that for class level, nothing changed. Still, all tests are selected. But for method level, we see that we are able to reduce the testing effort by 50 to 90%. And this, makes us conclude that the RTS effectiveness really depends on the precision of test specifications. Let's conclude. We presented microRTS and RTS approach for manual end-to-end testing in microservice-based systems. And I've discussed how we evaluated the performance, the efficiency, and also how we conducted an initial case study on a real-world microservice application, the Corona Warn app, and we provided some insights into RTS challenges in manual end-to-end testing. Thank you very much for your attention.